You know when you measure pressure with a gauge? Well, what if that number isn't what the molecules are actually feeling? Today, we're going to pull back the curtain on a really cool concept from thermodynamics called fugacity. It's all about the hidden story of how things really act when the pressure's on.
All right, here's the game plan. First, we'll look at why we even need something like fugacity, this whole ideal versus real-world mess. Then we'll nail down what fugacity actually is and get into this awesome idea of an escaping tendency. After that, we'll see how that helps everything find its balance. And finally, we'll wrap up with why this whole thing, why it actually matters.
All right, let's jump right in. We're starting with a classic problem that pops up everywhere in science. The battle between our perfect, clean models and, well, messy reality.
Okay, so in a perfect world, in our scientific models, gas molecules are just perfect. They're like little points zipping around, following all the rules, never getting in each other's way. Our equations, they love this. It's simple, it's predictable. But the real world? Real gas molecules are a whole different story. They're more like a chaotic mosh pit. They've got size, they're bumping, they're sticking to each other, they're pushing each other away. It's a total mess. And our simple, ideal equations just can't handle that.
So what do you do? How do you deal with that chaos? How can you possibly use those nice simple equations when reality is so messy? Well, scientists came up with a really clever workaround. Think of it like a secret weapon, a correction tool that helps us make sense of it all. And that tool is fugacity. So at its heart, fugacity is basically a corrected pressure. It's the pressure that the molecules feel like they're under once you account for all that pushing and pulling. And the beauty of it is, once you have this corrected number, you can plug it right back into those simple ideal gas equations, and suddenly they work for real stuff. It's the number that translates the chaos of the mosh pit into a language our simple models can understand. And the name itself is a dead giveaway to what's really going on here. Fugacity comes from the Latin word fugere, which means to flee. And that's not just some random fun fact. It's literally the key. It tells us that fugacity isn't just a mathematical fix. It's a measure of something real, something intuitive, the raw urge of a molecule to get out, to escape. Okay, so this escaping tendency, what does that actually mean? Let's really dig into that idea because it's how we can truly understand what molecules are trying to do, no matter if they're in a gas, a liquid, or even a solid. I mean, think about it like this. You're at a party, and the room gets super crowded. What's your first instinct? You want to get out, right? You want to escape to somewhere with more space. Fugacity is basically that get-me-out-of-here feeling, but for molecules. It's a number that tells us exactly how badly they want to leave their current situation, their phase, and move somewhere with a little more elbow room. So let's look at a low-pressure situation. The molecules are all spread out, they've got tons of personal space, they're barely interacting with each other, so they're behaving pretty much ideally. In this case, their desire to escape, their fugacity, is pretty much exactly what you'd expect from the pressure. The two numbers are basically the same. No drama here.
But now, let's crank up the pressure. We start squeezing those molecules together. Suddenly, they're all up in each other's business. Those intermolecular forces, the little attractions and repulsions, start to become a huge deal. Their behavior goes completely non-ideal. And that's when their escaping tendency, their fugacity, starts to go its own way. It's no longer the same as the pressure you'd measure on a gauge, not even close.
Okay, so we have this really cool way to measure a molecule's motivation. So what? What's the payoff? Well, it turns out this is the key to predicting one of the most important things in all of nature, a state of perfect balance we call equilibrium.
And it's beautifully simple, really. Nature hates imbalance. If the escaping tendency, the fugacity, is higher in one place than another, say it's higher in a liquid than in the gas above it, what's going to happen? Molecules are going to flee from the liquid to the gas. They'll keep doing that, moving from the area of high fugacity to low fugacity until the escaping tendency is exactly the same in both places. And when that happens, boom, you've reached equilibrium. Everything's stable.
So let's bring this all together. We've gone from this simple, ideal world all the way into the messy reality of how molecules actually behave. And we've seen that fugacity isn't just some abstract correction factor. It's an absolutely essential tool that lets us connect our simple theories to the real world.
Okay, so what are the big takeaways here? First, fugacity is that corrected pressure for real substances. Second, it's the true measure of that escaping tendency we've been talking about. Third, and this is crucial, it's the master key that determines when a system is in balance, in equilibrium. And that's not just academic. This is super important for chemical engineers, for geologists, for anyone who needs to predict how real materials will behave under pressure. At the end of the day, fugacity is the bridge that lets us use our simple, perfect models to understand our complex, messy reality.
So we've just seen that something as basic as pressure isn't as simple as it looks. There's a whole other layer to it. And it kind of makes you wonder, right? If even pressure needs a correction to match reality, what other perfect, simple laws of science are really just the beginning of a much deeper, messier, and honestly way more interesting story?